Hello everyone and welcome to this lecture in the Build Large Language Models from Scratch series. Today I am very excited for this lecture because we are going to look at how to load pre-trained OpenAI weights into the GPT model which we have constructed so that the text generation is coherent. This lecture will serve as a culmination of all the hard work which we have put in the previous lectures, because we are going to use the exact GPT architecture which we have built ourselves using this schematic which I'm showing you right now, and the GPT model class which we have defined in this lecture series. And we are going to integrate this model class with the GPT-2 OpenAI weights which they have publicly released. So let's get started with today's lecture. First, let me cover what all we have completed so far. Until now, what we saw in this pre training series is that we first saw how to define the losses for a large language model, how the cross entropy loss comes into the picture to find the loss between the LLM predicted output and the target sentence. Then we looked at the LLM pre-training loop itself, and we generated output text using our pre-training loop. The text which was generated from our loop was not very coherent. So let me just show you the text which was generated using our training. So this was the training loop which we had, and here you see that the input was every effort moves you, and the output was not very coherent. It was not making too much sense, and that is understandable because we had just trained this on one small book which was a very small data set, and we had run it for 10 epochs. Later what we saw was we integrated decoding strategies to reduce overfitting. The first strategy we looked at was temperature scaling, and then the second strategy which we looked at was top case sampling. Introduction of these two strategies definitely reduced overfitting a bit, but even then the next sentence which was generated, as you can see over here, did not really make too much sense. And now we have come to today's lecture where we are going to load the pre-trained weights from OpenAI in the hope that with the pre-trained weights from OpenAI, the next tokens which are generated, or the next token, or the next sentences which are generated, they start making a lot more sense. We are going to spend a lot of time in today's lecture in understanding, first of all, how to download these weights from OpenAI. Second of all, how to integrate these weights with our code which we have written already. So let's dive right into today's lecture. First, I would like to thank OpenAI for releasing these weights for GPT-2. The training itself might have taken around millions of dollars because the training has been done on a huge amount of data set, and these GPT-2 weights are now publicly available even on platforms such as Kaggle. So without access to these weights, today's lecture would not have been possible. And I would just like to take this opportunity to thank all of the LLM companies who are in the open source domain, especially, and who are publicly making available all the weights which are used by these models. Okay, so I'm going to take you to directly to code right now, and let me start explaining to you the different steps in the code. So previously, for educational purposes, we trained a small GPT-2 model, right? Which used a very limited data set. It was just a book. This approach allowed us to focus on the fundamentals, but we did not get coherent text as the our prediction. What we are going to do is that OpenAI has fortunately shared their weights publicly. So we are going to load these weights into our GPT model class, and we are going to use this model class itself for the next text generation. One thing to note before we get started is that OpenAI originally saved the GPT-2 weights via TensorFlow, whereas all of the coding which we have done so far in this lecture series is using PyTorch. So we will have to install TensorFlow, and one more library which we are going to install is called TQDM to track the download progress. So here you can see that in this line of code, I'm installing TensorFlow, and I'm also installing the TQDM library. The TensorFlow version should be greater than or equal to 2.15, and the TQDM library version should be greater than or equal to 4.66. So you can install both of these two libraries and then import them. So here I've printed the TensorFlow version and the TQDM version on my system. Once you install these two libraries, you can pause the video for the time being, and then you can continue with the rest of this video. Now comes the very important step of downloading the GPT-2 weights and their parameters. This is a step which still might be complex to so many students and engineers, so I want to explain this in a lot of detail. First of all, when you go to platforms like Kaggle, you will find files to download. So these are the 7 files which contain all of the information basically, and you will see that the file size is about 500 megabytes. But after you download this, there is a number of pre-processing steps which need to be done before the weights can be integrated with our GPT architecture. And I'm going to explain those steps to you right now. So let me take you through to the VS Code interface where we are going to look at this GPT underscore download 3 function, and or this code file, which will help us download these 7 files. And not just download, we are going to extract the parameters from these 7 files, and then we are going to store them in a very specific format. All right. So here you can see the GPT underscore download 3.py file. And first of all, you will see that when you open this file, it has 3 functions. It has the download and load GPT-2 function, which is the main function which we are going to look at. Then this function utilizes 2 helper functions. The first is called download file, and the second is load GPT-2 params from the TF checkpoint. So as the file names itself suggest, what this main function is going to do is that it's going to do 2 things. First, it's going to download the 7 files, these 7 files which I just showed you on Kaggle also. It's going to download those files and it's going to save them on my local computer. That's what it's going to do as the step number one. And then in the second step, what we are going to do is that we are going to take the downloaded file and then we are going to call this load GPT-2 params from uh, TF checkpoint. And what this function is going to do is that this function is going to store the parameters in the dictionary called as params. And this dictionary has a very specific format which we are going to see just in a moment. So just downloading the data from Kaggle is not enough. You need to understand the rest of the code and the format in which this params dictionary is returned. So let's start understanding this code sequentially. Before that, I just want to take a moment and explain these downloaded files. So once you run this code, you will see that you will get these files which are downloaded on your local machine. Without even running this code, you can even go to Kaggle and download these 7 files. Now, if a student has not been through this LLM lecture series which we have developed, they will not understand these files and they might seem a bit complicated, these files. But for us, for those students who have followed this lecture series, I want to show you that now these files are very easy to understand. So I want to explain each of these files sequentially. The first thing is checkpoint. So if you go to this file named checkpoint, you will see this thing called model checkpoint path. What this essentially means is that this is the path where all the current parameters, the weights of the GPT-2 model are stored. So you'll see that model.ckpt, we have 3 files named model.ckpt. The most important file is model.ckpt.data. This is where all the weights of the GPT-2 model are stored. So this checkpoint is just going to indicate the path at which the model weights are stored. The second file is encoder.json. So let me come to the top of this file. This file as a whole looks complex, but it's actually a vocabulary. It's a vocabulary of keys uh, and token IDs. So we have tokens here, and corresponding to every token, there is a token ID. That's the vocabulary which we are using. And if you remember the vocabulary size, it's 50257. So it starts from 0 and then the end of text is 50256. So there are 50257 tokens in our vocabulary. Then the second file is vocab.bpe. Remember, if you have followed this lecture series, we learnt about the byte pair encoder. It's a subword tokenization scheme, and the way this encoder works is that it looks for pairs of tokens which are occurring the most frequently, and then it merges this pair, and that becomes a token in itself. That's why it's called subword tokenizer. So this vocab.bp gives a list of the tokens which have been merged with the highest probability at the top. So all the tokens which have been merged have been mentioned in this list, and the tokens which come with the maximum probability, they are at the top of this list. So you might be thinking, what is this G dot, right? This G dot is a special convention which basically indicates that one token has ended and a new token has begun. So you can think of it as a space, and which marks the beginning of a new token. So it's a special convention used by OpenAI to indicate the end of one token and the start of a new token. Then the third file which I want to show you is hparams.json. This is the file which essentially contains all the settings of our model. The vocabulary size which we are using is 50257. The context length which we have is 1024. The embedding dimension is 768. What is the embedding dimension? Essentially all the token IDs which you see over here. If you see any token, every token has a token id, right? And every token id will be converted into a 768 dimensional vector space. These vectors are not trained, and our training will involve parameters corresponding to these as well. Then n heads. So n heads is basically the number of attention heads present in each transformer block, and n layer is essentially the number of transformer blocks itself. Now remember, these parameters, the setting values which I'm showing you, they are for the smallest GPT-2 model. When OpenAI made the GPT-2 weights public, they actually made the weights of their larger models also public. So 124 million, 355 million, 774 million, and 1558 million. The weights of all of these models were made public. But for the sake of simplicity, we are going to look at 124 million model right now, which had 12 transformer blocks. As you increase in the complexity of the GPT-2 model, the number of transformer blocks also increase. Remember that the same code which I'm going to show you today can be run for these larger architectures as well. Okay, so I hope you have understood the meanings of all of these files. Now, let us start going through this download and load GPT-2 code step by step and understand every single sentence. So the first thing is that we mention the URL. So we'll make a call to this API and we'll download these files. Download the 7 files which are present on my local computer right now. So the download file function will be called for this. And I'm not going to go through this in detail because this is just downloading the file onto the local machine. The real interest which I have is showing you what happens after the file is downloaded. So after the file is downloaded, first we have this tf checkpoint path, which is the latest checkpoint directory where all the model parameters are stored. So what this function will do is that tf.train, so tensorflow.train.latest checkpoint model directory. So it will go to our directory and it will look for this checkpoint, and it will look for this model checkpoint path, which is model.ckpt. So it will know where the model parameters are stored. Awesome. The next thing is that settings. We are going to maintain another dictionary which is called as settings. And what this settings dictionary is that it will exactly contain the same thing what is present in the hparams.json. So it will contain the vocabulary size, it will contain the context length, the embedding dimension, the number of attention heads, and the number of transformer blocks. So let me go back to the code again. Right. So this is the settings dictionary. And then in this last line of the code, this is where all the magic is essentially happening. And you really need to go into depth to understand what happens in this one line of code. So here what we are doing is that we are looking at the model path, which is given by this TF CKPT checkpoint, TensorFlow checkpoint path. And we are going to take the parameters from that path, and we are going to use the settings dictionary, and then we'll return a params dictionary. And the code which does that is this load GPT-2 params from TF checkpoint. So from the TF checkpoint parameters, we are going to load the parameters into a special dictionary called as params. Before explaining to you what is happening in this code, I first want to show you what the params dictionary looks like. All right. So here is how the params dictionary actually looks like. The dictionary will have 5 keys, which I'm going to show to you right now. What are these 5 keys and what do they exactly mean? The first key which this dictionary is going to have is WTE. The second key is WPE. The third key is blocks. The fourth key is the final normalization scale. And the fifth key is final normalization shift. To really understand these 5 keys and why do we need these 5 keys, you need to understand the GPT architecture. And we have spent a lot of time on this. I just want to summarize it quickly so that you can relate to these keys. So whenever a token comes in, whenever a sentence comes in rather, we have to first convert the input token IDs into token embeddings. So this will require weights. These will require parameters which need to be trained. Then we will need to add positional embeddings. These are also parameters which need to be trained. The result of token embeddings plus positional embeddings is input embeddings, and these pass on to the transformer block. So already you understood the purposes of the first two keys. This is for the token embeddings parameters. The WPE is for the positional embedding parameters. Now, after we get the input embedding, we have the dropout layer. Dropout layer has no trainable weights. So we don't have any keys corresponding to that. Then we move into this transformer block. The transformer block has several places where trainable weights exist. The first place is the multi-head attention layer. We have queries, keys, and the values weight matrices over here, right? And these matrices consists of parameters which we don't know. So this is one scope for trainable parameters. The second scope for trainable parameters is this feed forward neural network. Remember, this feed forward neural network has an input. So there is an input which comes in, then it passes through hidden layer. The number of dimensions in the hidden layer are 4 times the input, and then we have a final output layer which projects it back to the same size. So this first layer of the neural network is the fully connected layer. So I'm going to name it as FC, and the second is the output projection layer. So I'm going to call it as PROG. Both of these layers will have trainable weights. So that's the second scope for trainable weights. Now, if you look at the layer normalization 1 and layer normalization 2, let me highlight them with a different color. Layer normalization, let me choose purple color. So if you look at layer normalization 2 and if you look at layer normalization 1, normally layer normalization does not have any weights because we just subtract the mean and divide by the square root of variance, right? But the way we have defined layer normalization is that after we do the scaling, after we subtract the mean and divide by the square root of variance, we also multiply with a trainable parameter called scale, and we add a trainable parameter called shift. It turns out that these two parameters actually make a big difference. So that's why we have layer normalization 2 and layer normalization 1 also, which come into the trainable weight parameters category. And then we have the final output layer, the final normalization layer, which is another trainable weight matrix category. Wherever we have parameters to train, those are keys corresponding to this parameter dictionary. So you already saw token embeddings and positional embeddings. Blocks corresponds to all the trainable weights and parameters in this transformer block, in this blue color transformer block. And then G and B correspond to the trainable weight parameters in this final layer norm, which is indicated as 4 right now. So token embeddings, right? I hope you remember what are token embeddings. We have a vocabulary size of 50257, right? And corresponding to every token, we have a vector whose dimension is 768. So the size of this is 50257 rows and 768 columns. These are token embeddings. Now positional embeddings are governed by the context size. In GPT-2, the smallest model which we are considering, the context size is 1024, because maximum we can look at 1024 positions and then make the next token prediction. The 1025th position does not matter to us. So we only need embeddings corresponding to position number 1, position number 2 up till position number 1024. And these embeddings, each of these embeddings also has a dimension of 768. Because we need to add the token embeddings to the positional embeddings, the vector dimension of both of these need to be exactly the same, and that's there because it's 768 in both of these cases. Now, so this WTE key will have all these values corresponding to the token embedding matrix. The WPE key will have all the values corresponding to the positional embeddings matrix. Now let's come to the blocks. When you come to the blocks, there are several things which are happening in the blocks. So let me just rub this part a bit so that things are a little more clearer over here. Great. First, we are going to look at the masked multi-head attention, right? This has the query, this has the key, and this has the value. In GPT-2, when they release the weight, they fuse this into one single big matrix. So we need all the weights corresponding to this large matrix so that later we can split it into query, key, and value trainable matrix. So the way it is done in this blocks dictionary is that there will be a dictionary called, or there will be a dictionary called parameter. Within that there will be a keys blocks. This will link to another dictionary which has the keys transformer. This will link to another dictionary which has the keys h naught. Why h naught? Because there are 12 such transformer blocks. Remember, GPT-2 has 12 transformer blocks. So whatever I'm showed you right now, that will be replicated 12 times, right? So there are 12 transformer blocks. The first one is H0. Then there will be a key called ATTN. Why? Because we are looking at the attention mechanism, right? And then, and this attention mechanism also has the output projection. So we need to specify in the attention mechanism what we are looking for. In the attention mechanism, currently we are looking for CATTN. What is CATTN? It is the fused matrix of query key and value. And within this fused matrix, we are looking at the weights. So within this fused matrix, we are looking at the weights. So you see, that's how we access the weight matrix of the attention layer. So we look at the blocks key within that transformers. So let me show it to you here now. We look at the blocks key. Within that we look at the transformers. Within that we look at h naught, then attention, then C attention, which is the fused query key value, and then we look at the weights. Similarly, we do all this for the biases of the keys query and value. This is only for one transformer block h naught. We are going to repeat this for h1 h2 up till h11, since there are 12 such transformer blocks. So this is how you access the weights in the attention layers of the transformer blocks. This is how you access the weights and biases of the attention layer in the transformer block. And when I say attention layer, I mean the query key and the value weight matrices and the biases corresponding to each of these, right? So that's the first component which we looked at. The second component is this feed forward neural network. Now here, if you look closely, there are two layers. There is a fully connected layer and there is a projection layer. So we'll have weights and biases corresponding to this first layer as well as the second layer, and that is clearly mentioned here. If you look at the fully connect feed forward neural network, you have the transformer keys. Within that you have the h naught, which is the first transformer block. Within that there is a key called MLP, multi-layer perceptron, because we are looking at that expansion contraction neural network. Currently we are accessing the fully connected layer and the weights of that layer. Fully connected layer, the biases of that layer. So what I'm highlighting right now corresponds to the first, the fully connected layer, and its weights and biases. Similarly, to access the weights and biases of the projection layer, we just have the key as C underscore PROJ, and we access the weights and the biases. So this is how we access the weights and the biases of the feed forward neural network within the transformer block. Okay. And then usually at the end of the transformer, it's not shown here, but we actually have this output projection head. This output projection, and there are weights associated with that also. So to access the C projection in the, or to access the output projection layer, we just do transformers, then we go to h naught, the first block, then go to ATTN C proj, which is the output projection layer, and we get the weights. And similarly we do this for h1 h2 up to h11, so the 12 transformer blocks. So this is how you get the weights and the biases of the attention layers of the feed forward neural network and the output projection layer in the transformer block. But remember, the transformer block has two additional things. It has the layer norm 1 and layer norm 2, and both of these have trainable scale and shift parameters, right? So we need to access those. So the last thing which we are going to access in the transformer block keys, so this blocks keys, is that we are going to access transformer slash h naught slash layer normalization 1, then the scaling, which is denoted by G, and the shifting, which is denoted by B. This is the scale parameter and B is the shift parameter. Similarly, with respect to layer normalization 2, we will get the scale parameter denoted by G and we will get the shift parameter denoted by B. Remember that all of these are sub dictionaries within the blocks dictionary, and within this sub dictionaries ultimately we access the parameters. So if you look at the blocks keys, within the blocks keys, we are actually getting four things. We are getting the attention layer weights, query key value weights. We are getting the feed forward neural network weights. We are getting the output projection layer weights, and we are getting the layer normalization weights. So essentially with this, we get all the trainable parameters within the transformer block itself. Awesome. But our task is not yet over, because when we come outside of the transformer block, there is this final layer normalization, right? And actually, let me mark it with a different color. There is this final layer normalization. And similar to the layer normalizations earlier, it will have the scale and the shift. Now, remember that there are entirely different keys for the final normalization layer scale, and that's the key named G. And for the final normalization shift, there is an entirely new key which is called B. So the params is the dictionary, and then when you do params b, you will get the final norm shift parameters. And if you do params of G, you will get the final norm scale parameters. But to access, let's say, the attention head, what you will need to do is that I'm just showing a part of the code which lies ahead, but I think it is important to get the attention head. You will do params blocks, so you'll access the blocks keys, then you will specify that block number 1, 2, 12, etc. Then you will go to the ATTN keys, what we mentioned over here, ATTN keys. Then we will go to the CATTN keys, and then we will go to the W key. This is how we'll access the weights of the query key and the value matrices in the attention block, attention layers. So that's why we need all of these five keys which are returned by the parameter dictionary. So the whole goal of this load GPT-2 params from the TensorFlow checkpoint is to get the parameter values from this checkpoint, and then convert the parameter values into this params dictionary. So here you see we define the params dictionary, which is empty currently, and we first only define the blocks keys, and then we fill the blocks keys with every attention layer, the feed forward neural network, the output projection head. All of these are already present in the model checkpoint, but we just need to put them in the appropriate values. I'm not going to explain this part of the code, but because the main learning lies in you understanding these five keys. So this is how the blocks keys is filled up, and similarly all the other keys WTE, WPE, G and B, they are already present in this uh, model checkpoint path. So we just augment the params dictionary with all of those keys. So when you finally execute the load GPT-2 params from TF checkpoint, which is mentioned over here, the params dictionary will have those five keys which I mentioned to you on the whiteboard. This is what is happening in this piece of code. And then when you finish this function, you return two things. You return the settings dictionary, which consists of the vocabulary size, context length, embedding dimension, number of attention heads, and number of transformer blocks. And you also return the params, which is the params dictionary consisting of the five keys which I just showed to you on the whiteboard. I could have just skipped this part, but then I really wanted to show you the nuts and bolts of how the downloading is done. If you want to do research in large language models, it is very likely that you will need to download the pre-trained weights to do some testing or some training. And for that, you really need to understand the format in which GPT-2 releases these weights. If you don't understand the format, and if you don't understand how to convert this format into this parameter dictionary, it will be difficult to do novel research. So I hope you have understood this part. Now let me move back to the Jupyter notebook, and until now we have reached this stage where right up till here, where we will now, what we'll be doing is that from this GPT download 3.py, this Python file, we'll import the download and load GPT-2 function. It is this function, the download and load GPT-2 function. And then what we are going to do is that we are just going to run this function. We have to pass two things. We have to pass the model size, because remember that the model size can be 355 million, 774 million, and 1558 million also. And I encourage you to experiment with this after today's lecture is over. So we put in this model size and we specify the directory. So I have specified the directory to be GPT-2. So here you can see in the folder name GPT-2, all of my files have been stored. And then what you can do is that you can run this piece of code. So then settings dictionary, as we saw, we'll get the settings dictionary and we'll get the params dictionary when you run this piece of code. Now, when you run this, as I told you, this total size of all of this is around 500 megabytes. Initially, when I ran this code, it took a very long time on my laptop because my laptop kept crashing. It was not in a good internet area. And then I moved to another place where the internet connectivity was a bit strong. So here you can see I was getting speeds of 2 to 5 MB per second. And then this entire loading took around 5 to 10 minutes. So I encourage you to sit in a place with a good internet connectivity and don't restart your session or close your laptop during this time, because once this is loaded, the rest of the code proceeds in a very smooth manner. This is the most time consuming part of the code until this point. Now let's say this code is executed. After it's executed, since we have loaded this tqdm library, we'll see the progress which is happening. So here you can see that I've reached 100% in all of the different steps. So after this code has been completed, you can inspect things. You can inspect the settings dictionary and you can inspect the parameter dictionary keys. So if you print out the settings dictionary, you'll see that it has keys like nvocab, nctx, nembed, nhead, and nlayer. Now, as I mentioned, this is exactly the same as the hparams.json file here. It's just being converted into a dictionary now. And if you print the parameter dictionary keys, you will see blocks B, G, WPE, and WTE. We learnt about this exactly on the whiteboard, where we saw that the parameter dictionary will have these five keys: WTE, WPE, blocks, G, and B. Awesome. So I hope you have understood until this part where we have actually loaded uh, the GPT-2 architecture right now. We have loaded all of the parameters into our laptop and the parameters seem to be loaded correctly. What we can also do is that we could have printed the um, parameter weight contents, but that would take a lot of screen space. Hence, we only printed the parameter dictionary keys, not its values. But we can go a step ahead and look at the params dictionary and print out the WTE, which is the key corresponding to the token embedding vector. And we saw that the dimension should be 50257 rows, 768 columns. Let's just see if the dimensions make sense. So if you access the params dictionary with the key WTE, you'll get this tensor whose shape is 50257 and 768. At least the dimensions seem to be making sense. Great. So these values which you see on the screen right now, they are optimized values, which means that for every token, the token embedding weight dimension encodes some semantic meaning. Again, we should be thankful to OpenAI for releasing the weights publicly, because they would have spent about $1 million or even more for this pre-training. Awesome. So as I told you, we could have also downloaded the 355 million, 774 million, or 1.5 billion parameter, which is this release which GPT-2 had made, and you can feel free to experiment with that. But we have loaded the 124 million parameter. Now, before moving forward, one change which we'll need to do is, until now, when we use the GPT configuration in this lecture series, we use this thing called GPT config 124 million, and the configuration was almost exactly same as what's actually used in GPT-2, except that we used a context size of 256, whereas the actual context size is 1024. So we'll need to change that. So what we are going to do is that we are going to say that the new configuration is the same as our old configuration, but we'll update the context length to be 1024. And the second thing which we are going to update is the query key value bias. So when we trained the attention mechanism and when we run our own LLM before, we have put this query key value bias to false. But in GPT-2, this was actually put to true. So we are also going to put this to true. Here I've added a small note that bias vectors are not commonly used in LLMs anymore because they don't improve the modeling performance and they are not that necessary. However, since we are working with pre-trained weights, we need to match the settings for consistency. And that's why what we are going to do is we are going to enable the query key value bias to be equal to true, and we are going to use the context length to be 1024. So then we create an instance of the GPT model class with this new configuration. I just want to show you the GPT model class which we have so that it is on the screen. In case you're coming to this lecture for the first time, we have developed a GPT model class which looks something like this. Yeah, this is our GPT model class. uh, and now the main goal which we have is how are we going to integrate the weights which we have downloaded with the GPT model class which we have defined. So let's learn about that a bit. So there is a specific way in which we are going to do this integration. So look at the GPT model class. What we are doing currently is that we are just initializing the token embedding matrices, the positional embedding matrices, the transformer blocks weights. We are initializing them to random values. But now our main goal is that the weights which we have downloaded from GPT-2, and which are currently stored in this params dictionary which we have returned, we need to somehow make sure that these weights are integrated with our GPT model class, and instead of these random initializations using nn.embedding, we actually make the initializations from the downloaded GPT-2 parameters. So for that, we first need to look at the transformer block, and I want to show you a couple of things in this transformer block. So I've just control F here and searched for the transformer block. Yeah, so here is the transformer block. Okay, what we are going to do in the code is that here you can see that there is a object called attention. So that's a instance of the multi-head attention class. What we are going to do is that we are going to take this object and we are going to make sure that when you define this ATT object, the query key and the value matrices are assigned to the query key and the value matrices which are obtained from the parameters dictionary, from this dictionary over here, this the attention layers from this dictionary. Similarly, when we look at the feed forward neural network FF object, we are going to make sure that this feed forward neural network receives values from this feed forward neural network weights dictionary which we have in the parameters dictionary. So let me again take you back to the current code. It's a bit down below, but let me scroll down below so that um, you understand what's really going on. Awesome. So now what we are going to do, as I said, is that we are going to link our GPT model class with the downloaded weights from OpenAI GPT-2. So the way we are going to do this is that first let's take a look at the attention block, right? Let's take a look at the attention block and let's take a look at the queries, the keys, and the values. So what we are doing here is that first let's access the queries, keys, and the values downloaded from OpenAI GPT-2. And the way to access it, as we have already seen, is that you go to the params dictionary, you go to the blocks keys, then you go to the transformer sub keys, the H0, the ATTN, the CATTN, and the W. This is exactly how we are accessing these weights. But remember, these weights are a fusion of queries, keys, and the values. So we are going to split these along the columns, and then we'll get the queries weight matrix, the keys weight matrix, and the values weight matrix. As I told you before, we are going to get the ATT object. Remember, I showed you in the transformer block class the ATT object, and then in that object, I'm going to assign the queries, the key, and the value weight equal to the q underscore w, the k underscore w, and the v underscore w, which has been obtained from OpenAI GPT-2. That's it. It's as simple as that. This right here is the assignment step, and the assign is the function which we have defined here. What this assign does is that it takes left and right, and it will first check whether these two values, the shape is matching, and if the shape is matching, we just return the right values, which means the left is just assign the value equal to the right, and then we return it. If the shape does not match, it will give us an error, and that means that we are not loading the GPT-2 weights correctly and not assigning them correctly. So this is the part where the where the attention block query key and the value weight matrices are updated. Similarly, in this part, the bias is updated. So it's the same as the earlier part, but then W is replaced with B to update the bias terms. Now, if you look at the transformer block, there are other things also. There is this output projection layer, which is accessible to through transformer dash H0 dash ATTN dash CPROS dash W. So what we are going to do is that again we are going to access this output projection layer weights, and we are going to assign these weights downloaded from OpenAI to the ATT dot output projection weight. So we are going to look at the ATT object again, and then we are going to assign output projection weights equal to what we have downloaded. And this is the same for weights as well as biases, right? Then we are going to look at the feed forward neural network. What I'm highlighting on the screen right now is for the first layer, which is the fully connected layer. As I've shown over here, the feed forward neural network has two layers, the fully connected layer and the projection layer. So in the fully connected layer, what we are doing here is that we are accessing the weights and the biases of the fully connected layer from the GPT-2 downloaded values, and then we are assigning these weights and biases to the FF object which we saw in the transformer block. So that way the neural network, the fully connected layer weights and biases are equal to the GPT-2 downloaded weights and biases. Now this same thing is done for the second layer, which is the projection or the output layer of the multi-layer perceptron or the feed forward neural network. And then finally we come to the last puzzle, or the last building block of the transformers rather, and that is the layer normalization. So there are two layer normalization, the layer normalization 1 and layer normalization 2, and both have scale as well as shift, right? So this is what's happening here. What I'm highlighting right now, we are accessing the shift and the scale parameters from the GPT-2 downloaded, and then we are assigning those parameters to our GPT model class. And what I'm highlighting on the screen right now is this similar process done for the second normalization layer, which comes after the attention mechanism in the transformer block. Okay. Now, when we come out of the transformer block, you see there is another normalization layer, right? The final normalization layer, and it just accessible through G and the B keys. So what we are doing is that we are accessing the params G and the params B, and then we are assigning our GPT model class scale and shift values to whatever is downloaded from GPT-2. Now you must be thinking that, okay, there is, if I look at the architecture closely, there is this final layer, there is this linear output layer, and careful readers might remember that this linear output layer also is a neural network. And where do we get the dimensions? Where do we get the weights of these? We did not download this from GPT, right? So the way GPT-2 was designed is that it uses this concept of weight tying, which means that the token embedding weights are used for constructing this output head. So the same token embedding weights are used for this output head layer. So we don't have to define any new weights for this layer. We recycle the same weights what's used in the token embedding. Weight tying is not used these days too much, but it was used in the GPT-2 architecture. And so we are also using the concept of weight tying. That actually brings the total parameters from 162 million to 124 million. If you don't do weight tying, the number of parameters will be 164 million. Awesome, right? So what we have done here is that until now, this piece of code over here, load weights into GPT. This code, what it does is that it takes two values. The first, it takes the instance of the GPT model class, and the second, it takes the params dictionary. So it takes this dictionary, which essentially contains this dictionary, which essentially contains all the weights of GPT-2, and then it just assigns all of these weights into the GPT model. That's what this load weights into GPT is doing. And now if you see above, we have already created an instance of the GPT model class, and if you scroll even above, we have already got the params dictionary. Awesome, right? So now we just need to call this function, and that's exactly what we are doing here. We are calling this function load weights into GPT. What this function does is that it takes the params values, and then it which are downloaded from GPT-2, and then it loads into our GPT model instance, which means that our own GPT model, which we have constructed from scratch, is now fully ready. It's fully functional to be tested. So now let's go ahead and do the most exciting thing in this lecture, which you all have been waiting for. Let us test our model, which we used our own architecture with the GPT-2 pre-trained weights, and let's see what the output is. Great. So now let's go ahead and test our model. So here you can see that here is the generate function, which basically generates new tokens, and we are passing the model which we have defined, and that this model now has the weights which have been downloaded from GPT-2. The input token IDs are every effort moves you, and the maximum number of new tokens is 25. I have defined the temperature not too high, 1.5, and the top K is 50, which means that 50 tokens will have the chance or the opportunity to be in the among the maximum new tokens, or to be in the generated token. So before we see the output for this, let me show you our performance without using GPT-2 weights. And here you can see that if we do not use GPT-2 weights, we were getting something like this, which did not make any sense at all. And now what we are going to do is that we are going to run this right now. So I'm going to run this live, and just to show you that once you load the weights, the running actually, this code does not take too much time, because we already have pre-trained weights. So here you can see with the star symbol that it's running right now, and now it generated. So every effort moves you toward finding an ideal new way to practice something. What makes us want to be on top of that? This is incredible, right? This output sentence is much more coherent than what we had obtained earlier. So right now in this lecture, we have built our own GPT from scratch, and it seems to be working. That's incredible. All the other students which have not been through this course or who have not seen these lectures would be just using chat gpt, but now we have built our own gpt from scratch. Isn't that incredible? It took us a long time to get here, and code length is also um, the code length is also pretty large, so you can scroll above and see how long the code has become, but it's all worth it because we have learned how to build gpt from scratch. Now what you can do is you can go ahead and do your own research. So for example, if you want to change the temperature value to 10, I know that this is not good, but I want to see the effect of a higher temperature value. We cannot do this using chat gpt, right? But now since we have built our own gpt, we can explore with so many things. So here you see I've increased the temperature value to 10, and let's see the output text which is coming right now. Ideally it should be a bit random because increasing the temperature increases the entropy. Now see the output. Every effort moves you towards finding an ideal new set piece, but only at times or for hours I was working on my first game called G. So as expected, increasing the temperature has given me random outputs. But you see now this opens the door to so much more creativity, hyperparameter tuning. Even you can do research such as small language models. What if you want to change the architecture? You can now easily go ahead and change the architecture, right? All you need to do is that you need to go to this gpt model. Once you have understood the code, once you have seen the previous lectures, you need to go to the gpt model which we have defined. So here is the gpt model right over here, and then you can add or subtract a few layers. What if we don't need 12 transformer blocks? What if you want to test with a smaller language model? All of these experiments now remain open to you. So this lecture series is also the pathway for you to become a large language model researcher or a machine learning researcher, because now you have something which works on your local computer and runs in a fast manner. You can do iterations, you can test. So if you want to test the effect of top k, if you want to test the effect of maximum new tokens, if you want to vary the number of attention heads, the number of transformer blocks, the optimizer size, you can even vary the optimizer step size. So for example, we have used adam, right, with the learning rate of 5 into 10 raised to minus 4, weight decay of zero point 0.1. You can even change this and check the output. All of this is now accessible to you. So that's why I believe that we have achieved a significant milestone completing this lecture. If you have come to this lecture for the first time without watching the other videos in this lecture series, it's amazing. But now please go back and try to watch all the other videos to master your concepts, to become a very powerful llm engineer who is creating new norms, who is really doing cutting edge research. You need to know the nuts and bolts of how the modeling process works. And I hope that through this whiteboard approach and through this coding approach you are getting exposed to those nuts and bolts. I've not seen any other content out there like this currently. That's why it's very hard for researchers to even download or load publicly available weights. So I'm trying my level best to teach you every single thing by not making short videos but by making longer format videos like this one. And now we are confident that we have loaded the weights correctly. Why? Because the model is producing coherent text. So again, let me switch the temperature to zero point 0.1, and let me run this again. So now I'm running this, and as you see earlier, when the temperature was, I think it was not zero point 0.1, it was 1.4. We'll need to run this again for 1.4. But if you see for zero point 0.1, again the model is quite good. But even I'll do for 1.4 because we started with that condition earlier. So we are confident that the model weights are loaded correctly because the model can produce coherent text. At least the words make sense. A tiny mistake in this process would cause the model to fail. Now, in the next chapters, what we are going to see is that now that we have mastered pre-training, we are going to look at fine-tuning. So the LLM subject does not end at pre-training. After getting this model, let's say if you want to build a text classifier, let's say if you want to build an educational quiz app, which is a very specific application, how can you use the pre-trained weights? How can you fine-tune these weights so that it's specific to the application which you are building? We are going to learn about this in the next lecture. So all the next lectures are going to be very interesting since they are going to be application oriented, and for all of those we are going to use this gpt model which we ourselves have built, not relying on any other gpt model. And that gives us a lot of confidence as a large language model or a machine learning engineer. So thanks everyone for this lecture. This was a bit of a long lecture and also a dense lecture, but I hope you understood everything which I was trying to teach. Please try to reach out or comment if you have any doubts or any questions, and I'll be happy to discuss this further. And I'll also be happy to see what all research you have worked on by using this code file which I'll share with you. Thanks a lot, everyone, and I look forward to seeing you in the next lecture.